light somehow makes it across the universe. Light can travel a very long distance, and it doesn't lose its oomph. It clearly maintains its color, its frequency, as it goes. Somehow, it has this property that somehow it can travel through the universe itself. And if you think light is just a bunch of particles, that might not be so surprising. If the universe is mostly empty, and you're sending bullets through it, well, the bullets will just keep going, according to Newton's first law.
Yeah.
Nothing there to stop them or slow them down. But there was a debate for 2 centuries as to whether light was a wave or made of particles, and then around 1800, there was definitive evidence from interference effects that no, light is really a wave. And now we hit a puzzle. So if light waves can go through the universe, there must be something out there. There must be a thing, that you would naturally think, that is vibrating, that in which the waves are a vibration. So what is this thing? And why doesn't it slow the Earth down? I mean, at a certain level, we don't entirely know the answer. The point that seems obvious is even if you're confused about what this stuff is, you should be able to measure whether you're moving through it or not. For example, if you're in a boat, you can easily tell if you're moving through the water or not. If you turn off your engine, if you're moving through the water, you will very quickly slow down. And although Galileo says you can't measure whether you're moving in a steady motion, if you're slowing down, you certainly feel that. So you can tell whether you are in motion and how you are in motion with respect to ordinary substances. So the basic idea was we ought to be able to tell if we're moving through this magical substance, which was called the luminiferous ether. The idea was, all right, there should be some measurement we can make that can tell us something about this substance in which light is a wave. And in the 1880s, the right technology came along, and that was invented by Albert Michelson, who, along with Edmund Morley, built a machine, a device, that could very accurately measure the speed of light in different directions. And if you think about it, if you're moving through the water and you're looking at ocean waves that are going in the same direction that you're going will seem, relative to your boat, to move more slowly than ocean waves going the other direction. And so it was a similar idea that Michelson had in mind, that you should be able to tell that light moves at different speeds relative to this medium, depending on how fast the Earth is going through the medium. And of course, the Earth goes in different directions as it goes around the sun. So if you measure this a few times a year, or you measure this in different directions, you should be able to tell a difference. And famously, Michelson and Morley saw no difference at all. The speed of light seemed to be the same from all directions at all times. And that seems to be in contradiction with the idea that there's a substance in which light is a wave. Now, this is where we come back to Galileo. Because if it had been true that Michelson's experiment had worked, if it were possible to tell how fast the Earth were moving through this luminiferous ether, then it would not be true that all types of steady motion are the same. There would be experiments that you could do, even in a closed room, even under the deck of a ship, as Galileo suggested. There would be experiments you could do. You could do Michelson's experiment and tell how fast you are moving through the ether. But since the ether apparently is everywhere in space, after all, light goes through the universe from all directions and many places, then you would conclude that Galileo's idea, although it might apply to some things, is not fundamentally correct. And so Michelson's experiment, had it shown a difference in the speeds of light from different directions, would have been the death knell for Galileo's relativity. So now came a brief period of 25 years where people tried to explain what does Michelson's experiment mean? Why can't we detect this thing? And there were various ideas which we don't have to go into, but all of them would still have violated Galileo's relativity. And then Einstein pointed out, as a 26-year-old student, that actually, if you insist that Galileo's relativity is correct, and you relinquish your notions of space and time as you always thought they were, you can write down math that is that can both explain why light travels as a wave, in particular a wave of the electromagnetic fields, and yet can travel from your perspective at the same speed from all directions, independently of how you are moving or the object that's emitting the light is moving. And that was an extraordinary thing to point out. That's obviously one of the great ideas in scientific history, because it showed that the only way to reconcile light's amazing ability to travel the universe is to give up your notions of how space and time work. Einstein's theory of relativity is not the invention of the idea of relativity. It is a revision of the idea of relativity as Galileo had it. Because Galileo didn't worry about time. Galileo just worried about how things move, but he assumed time is just time.